Good evening, great. Everyone's coming relax. It's end of the day. Everyone should be have a full day. So I hope everyone get his coffee and coming relaxed to start the session. Our session today will be about the basics of ASCP technology. Okay, don't be in rush to have a lot of information in the beginning because we have many slides and the information will coming during the time. So don't be in rush to ask for a question if you need more clarification. But if you have any question related to the same slide, please feel free to interact at the end of the slide in order to respond to your questions. Our agenda today will explain why we need to have an artificial lift. And then we will go to the ESCP main components overview, and we'll go for each component from ESCP in details. What is the component for each part and what is his function, and when we can select each part for their purpose. We'll go for pump, intake, and gas separator, and seal section, and motor, and ended up by surface equipment. Let us start with safety moment. Currently, a lot of people, as we see already on the street and everywhere, getting relaxed while the COVID is still there. So it's a reminder again, COVID is still there. COVID Delta is much dangerous. So please don't relax. Stay follow up on all COVID regulation. Don't touch your face. Wash your hand often. Get alcohol. Stay at home if you feel you are sick, and use sanitizer, and don't keep any parts from home subjected to this infection, and make sure you disinfect your home in regular basis. And for sure, on the top of all of that, you have to get vaccinated. And if you don't have vaccination yet, please hurry and get vaccinated. And also, vaccinated people shouldn't be on relax. They are vaccinated because vaccination might affect only the side effect will be a little bit less, and the symptoms will be much less, but not meaning if you are vaccinated, you will not be subjected to have again and again. Please make sure you follow COVID regulation, get vaccinated, stay safe, you and your family. Okay. Why we should have an artificial lift? Initially, for any new oil, any new wells, the pressure for reservoir is coming in a high value. So the pressure for reservoir is enough to deliver the fluid to the surface. But after some times, there is a decline on reservoir pressure. So we have to get the tools to compensate the decline of reservoir pressure. That's the first reason why we need to have an artificial lift. Number two, at some cases, okay, the reservoir pressure is not giving an acceptable rate to the surface, or so we have to bring the artificial lift in order to deliver the required flow rate to the surface. If you produce with minimum rate, okay, less than the acceptable rate, so you will have a consequence of water cooling or of sand production. So you have to get the artificial lift in order to get the optimal production rate. After years and years from starting the production, the water cut increase, and that affects the production and make something called water loading on gassy wells. That's why we need artificial lift to do some action called dewatering on some gas wells. So this is the third value and requirement for artificial lift. Number four is to overcome the high friction pressure associated with the tubing production inside the tubing from producing high viscous oil and waxy oil as well. Also, artificial lift is needed in order to reduce the effect of flow line back pressure. If we have multiple flow line already connected together, some of those flow line having a high pressure, while we have one well producing at low wellhead pressure, that might affect the production in terms of rate and in terms of performance as well. So artificial lift.
باشمهندس في مشكلة في الصوت يعني عند حضرتك ممكن try another connection.
Okay. That was much better. Okay.
Okay, go ahead.
And one of the most important value for artificial lift and for ESP as well is to maximize the production rate, is to get the maximum output from your reservoir. And the last one is to deliver high wellhead pressure to transfer the oil, and this especially on offshore application on for far and marginal fields to deliver a high wellhead pressure. In terms of electrical submersible pump advantage, the advantage for electrical submersible pump is to deliver high volume, which is best in class in that field compared to rest of artificial lift, compared to beam pump, Pcb, jet pump, all of other artificial lift cannot be compared with ESP when it comes to higher fluid volume capability. And also can be connected with downhole sensor in order to have a real-time monitoring. On the rest of artificial lift, you cannot get the full downhole parameter. On Pcb, you can get, for example, only intake pressure. You cannot monitor the temperature. Or on sucker rod pump, you have less parameter can be monitored. For ESP, it is a unique artificial lift, can get a full parameter to be monitored, make sure you have the optimum performance and have a real-time optimization immediately upon the sensor data. And also ESP can be installed on deviated and horizontal well, sometimes reach up to 65 up to 70 degree inclination, and sometimes reach up to 15 dog leg per 100 meter. So this is one of the per 100 feet. So this is one of the advantage for ESP as well. In terms of corrosion and scale, ESP can fit with chemical injection, either to have a separate chemical injection or combined with ESP. That's one of the advantage for ESP. In some other artificial lift, such as Pcb, you cannot inject a downhole chemical because that affect the integrity of those artificial lifts, such as elastomer effect. Also, the ESP have a wide range of size and a wide range of size in terms of OD, in terms of capacity, in terms of technicality, in terms of application. So you have the variety and not limited, such as the rest of artificial lift. You have almost 3 or 4 category only per each technology of the rest of artificial lift, while the ESP is not. You can have almost hundreds and hundreds from application on each type of equipment. And the lifting cost for higher volume is compared to other artificial lift will be quite low. And make sure you are careful when you are comparing the cost per barrel. Cost per barrel, for example, if you have one well producing 100 barrel oil and other well producing 2000 barrel oil, so you cannot compare both of them. You have to compare apple to apple. So you have to compare one well producing with ESP for 2000 barrel
and one well producing 2,000 barrels with PCB, and compare the cost associated for both scenarios, that will be apple-to-apple comparison. At that, you will have an efficient cost per barrel for ESP. The limitation for ESP, and also it's really important to know those limitation is minimized year by year because of the R&D and technology and research is keep running day by day in order to overcome those limitations and have a new technology that can be installed on those limitations. Number one is the deterioration of the cable due to high temperature. Nowadays, the maximum downhole cable can be installed in downhole application up to 400 F. So above that value, you will be tight hand to install ESP. With those 400 F, you can reach almost up to 15,000 feet of depth based on the geothermal gradient. Also, ESP almost required to have a large casing or bigger OD. It's better to have a bigger casing. Sometimes is installed. It can be installed inside 9.58 inch. It can be installed in 7 inch. It can be installed in 5.5 inch. Below 5.5 inch, you have to install slim equipment. So if you have a 4.5 inch casing, you have to install a slim downhole equipment, which is not the popular equipment and have its limitations. So case by case, you can install the ESP on 5.5 casing and above. Less than 5.5, you have to install special equipment, which is called slim downhole slim equipment. Most of the ESP system is installed downhole. So if you need to make an well intervention or you make to pull the downhole equipment and install it again, you have to call a rig. So without rig, you cannot retrieve and repair the ESP equipment. There is some application of rigless ESP equipment, but nowadays it's only installed on high profile wells, such as offshore wells with high production in order to have an efficient cost per barrel. But up to date, the ESP required a rig in order to be pulled and repaired. ESP is only applicable when you have an electrical source. If you didn't have an electric source, you cannot install ESP. And there is a risk of high voltage, and that's one of the risks on ESP. So you have to get a trained personnel in order to be qualified to deal with the existing risk. And also the surface equipment, which we will go through, required to have enough space to be set up, and those space might be some limitation on offshore field, and you might change from some equipment to another in order to fit with the existing offshore skid. The area for ESP to be installed in, as we spoke, on high volume oil well, on offshore application, in deviated wells, in very sensitive area, because the ESP have almost zero spill compared to other artificial lift such as PCB and ESP. So when it came to agriculture sensitive area, when it came to environmentally sensitive area, you have to go for ESP because of HSE regulation. You are not allowed to have an oil spill. With the steam application, you have to install ESP because the rest of artificial lift have a limitation with the steam. Also, it's applicable on dewatering, on mine and gassy application, and coal bed methane and geothermal wells. It's a high-tech application, and also utilized on water handling and water injection and reservoir pressure build-up application and surface handling as well. On that schematic, this is the main component of ESP system. will go from bottom up. Starting from bottom, you have your downhole sensor, then the motor, then you have your seal, and the pump is connected to the intake, and power cable up to the surface. You have the junction box, transformer, and power and VSD. And depend on the application, you might have another transformer or not based on the existing power source. In order to get an overview on the entire ESP equipment with the name of product related to Baker Hughes, okay, each company have the name of the product. But on the previous slide, we talk in generic. There is a pump, there is seal, there is a motor, but there is no name for the product. Baker Hughes equipment is rotating clockwise, okay, while the rest of other ESP service provider is rotating anti-clockwise. So Baker Hughes have two types of surface equipment or VSD. One is called electro speed advantage and other one is called vector plus. And then the power cable is called center line cable. And then when we go through the pump, we have the flex pump series and left prime pump. And MVP, which is abbreviation for multi-phase gas handling pump, and S pump, S plus, which is gas handling device, and gas insurance, which is also for gas handling, and gas separator, which is for handling the gas, and seal, which is called center left SP and XP seal. And we have our center link MLE portfolio. And going to the motor, we have SP and XP motors, and the downhole sensor, which is called Zenith down.
We have the full pictures of ESP component, and we will go for item by item through each component in details, and it explains the cycle of operation of ESP. Any question on the previous slides before we go for each component and explain the cycle of operation and function for each part?
Okay. The first one on our ESP component will be the pump. The ESP pump is a multi-stage centrifugal pump. Is required some component as already showed on the schematic. Housing, which is the outer body of the pump, and shaft, which is the axe pass through all the entire centrifugal pump, impeller and diffuser, and connected to the bottom of the pump, we will have the intake. Okay. The ESP is utilized. The centrifugal force is to convert the energy from the rotating shaft in order to lift the fluid to the surface. Almost the pump will be connected from the top to the production tubing, and from bottom will be connected to the intake. In order to have some photos, in order to imagine how it looks like each stage, on the left hand side, on the bottom of the slide, you can see the one stage pictures, and on the right hand side you will have the two parts for each one stage, which is called impeller and diffuser. So each impeller and diffuser combine together to form one stage, and each stage connected to the rest of the stage and combined stacked together inside one housing along the shaft in order to form the one section pump. Okay, those one section pump, it could be connected from the top to the discharge head, which is connected to the tubing, and from the bottom, it could be connected to another section of pump if you need a multiple section, or it could be connected to the intake directly. Okay, in terms of the classification for each component impeller, as you can see, there is a cutway of the impeller. The impeller is key to the shaft and rotate at the same motor RPM. This impeller rotate with the centrifugal force on the production fluid, and the fluid goes through the impeller and then to the diffuser in order to create the kinetic energy, which is going to the second impeller as it's shown on that schematic by rotating the shaft. So it provides centrifugal force to the fluid and gives that kinetic energy to the next stage. The fluid goes into the impeller through the eye near to the shaft end, as it's explained on the schematic on the right hand. So the fluid goes from the bottom inside the impeller through the eye and then go to the next stage. Okay, on the left hand side you can find the real photo of impeller and the parts and classification for each part of impeller. On the right hand side you can find the schematic, but in drawing, the top side is the hub, and then you will have the upper shroud in the vans, in the van, which is the height of vary from one stage to another based on the application, and the lower shroud and the skirt and the eye, which is the inlet for the fluid. On the left hand side you can have the different color, which is called up thrust washer and down thrust washer. Okay, this the down thrust washer and up thrust washer, we will came to that part to in order to clarify the function for those parts in detail. Okay, then we will go to the diffuser. The diffuser, after we have already the fluid inlet to the impeller and it's formed a kinetic energy. This kinetic energy, when it goes to the diffuser, it already converted to potential energy, which is accumulated until it reaches the discharge head and forms the discharge pressure value. Okay, you have to be aware the impeller is rotate with the shaft with the same RPM of the motor, while the diffuser is not. So please make sure you already understand that the impeller is rotating with the shaft at the same RPM, while the diffuser is not. It's fixed. Okay. And according to the illustration on in the schematic, you can find the way of the busway for flow. It goes from the bottom of the impeller through the eye and then go to the diffuser. And then impeller and diffuser is stacked together, and the diffuser is directly direct the fluid into the eye of the next impeller, and then the impeller with the rotation it spin and gives the energy to the fluid, which exit around the outside, and the diffuser will be lift the fluid up to the surface in order to bring the required head value in the pressure up to the surface. With that, we already explained how the fluid is going through the impeller and diffuser and how the energy is transferred and stored in terms of kinetic energy and then transferred to potential energy, creating the required head and deliver the required value in order to lift the flow to the surface. That is the theory of operation of ESP, illustrated in photos and in busway of fluid. I hope that is clear, because with that, we should go for the details in the pump stage hydraulic design. If something was not clear on the theory of operation of ESP, if something was not clear on the impeller and diffuser difference and internal parts and function for each part, please may be realistic and come up with question in order to be clarified before we go to the next slide. Okay. With that, we will go to the pump stage design in terms of hydraulic. The pump stages in terms of hydraulic, it can come in 3 different categories. Those 3 different categories, either a radial pump or mixed pump or axial pump stages. So the design for each impeller, it could be vary either radial or mixed or axial. So what is the difference between each type of those pumps in terms of hydraulic design, and when we have to select each one of them based on which application? The design of submersible centrifugal pump, as we spoke, okay, it has the radial and mixed flow design. The smaller flow pump are generally coming in radial flow design. So when we talk about 100, 200, 300, up to 1,000 barrel, it's almost coming in radial flow design. At some company, they call the radial flow as pancake. So it's called pancake. If you look for the red illustration on the photos, you can find the flow inside the impeller at close to 90 degree. Okay, so the flow is go inside the diffuser and then up to the impeller and then to the next diffuser in a 90 degree shape. So that is the radial flow design. Okay, so when we have to use that radial flow, almost as we in low rate application. So it's used on low rate application. Okay, next one is the mixed flow stages. The mixed flow impeller, if you have the same illustration on the photos, it's the flow busway is almost close to 45 degree. So those almost utilized on the high rate application. Okay, and the third type of hydraulic design is called axial flow stages. If you look for the blade of those axial flow stages, you can almost have there is no any inclination on the build up of the pressure. So those axial flow is not utilized is to build a pressure, is utilized only to handle gas, so or separate the gas. So in terms of ESP pump, axial flow is not utilized at all in any ESP pump design. Is only utilized for gas handling, for gas separation, and multi-phase pump application. Okay, I hope that clear. And then we will clarify if you need to select a radial flow or mixed flow, what was the advantage and disadvantage for each one. Okay, so when we talk about radial flow, if you look for the flow busway, it's 90 degree and that can be easily to be plugged. So if you have a well conditioned with paraffin, with wax, with sand, with any plugging material supposed to plug your system, radial flow is not recommended to be installed, because with that pathway of fluid, it will be easy to be plugged. So don't use those type of design with the well fluid expected to have a plugging with some sort of deposits. Okay, the radial flow is handling almost 10% of the gas into pump. So if you have a well condition with almost 10% of the gas free, radial flow can handle that gas without the need of gas separator. But if you have the gas in pump is higher than 10%, radial flow shouldn't handle and will not be able to handle that without the help of gas separation or gas handling device. Okay, there is a one of advantage of radial flow over the rest of stages design, such as axial and mixed as well. If you look for ESP design to produce 1000 barrel fluid, for example, and you calculate the number of stage from that radial flow stages compared to mixed flow stages, you will have less number of stage. For example, let us say you will utilize 20 stage from radial flow compared to 35 or 40 from mixed flow. So the radial flow is good in terms of pressure build up and in terms of production optimization. So radial flow is a lot of benefits when you talk about production optimization compared to mixed flow. So if you have one well without any possibility to have the plugging expected, without gas issue, without sand issue, so it's better to choose the radial flow stages over the mixed flow stages, because it will require less number of stages and will support a better handling for production optimization in the future. Okay, with mixed flow, if you look for the busway, it will be difficult to be plugged compared to radial flow. So that mixed flow stages is recommended to be utilized on the application while you are expecting to have a plugging. When you are expecting to have sand plugging, wax, scale, paraffin, whatever the deposits that you are expecting or you are having experience with your field, so you have to use the mixed flow stages. Mixed flow stages is handle almost 20% gas into pump compared to radial flow, which we are just talking, it handle only 10%. So it's handle almost double the value for radial flow. In terms of weight, the mixed flow weight for each stages, you can truly imagine the weight for each stage for mixed flow compared to radial flow, it almost higher. So it create higher thrust compared to the radial flow, which we will explain later on the thrust discussion. With that, we already explained the three different type of pump stages in terms of hydraulic design: radial, axial, mixed, the difference between each one of those three category, when you need to select the radial, when you need to select the mixed, when you need to use the axial. And that is almost covers the difference between those three categories in terms of stages hydraulic design. Any question before we go to the next topic, which is related to stages design in terms of assembly and construction? Okay. The pump stage in terms of assembly or construction. Okay. When we talk about hydraulic design, that means the flow pathway inside the impeller and diffuser. But when we talk about the stages construction, how we will connect each impeller to the shaft, to the diffuser, and stacked all together. So the final assembly for entire pump section, how it looks like. We have two category of pump stages assembly and construction. The first one is the floater pump design. and the second one is the compression pump design. With the floater pump design, the impeller are free to move up and down with the along the shaft with the energy of fluid itself. So if you have high fluid coming from the reservoir, it will push the impeller up. And if you have no flow, it will stag down. Okay, with the gravity and the weight of the impeller itself, it will be going down to the diffuser. Okay, with the compression pump design, the impeller is locked. Okay, and is not free to move down, but it's free to move up. So the impeller itself is locked to prevent the axial movement along the shaft. In floater design, each impeller have the weight is absorbed by the bottom diffuser and thrust bearing as well. But in compression pump design, all the thrust of each stage along with the shaft is transferred to be supported by the seal section thrust bearing. So that's a major difference between the floater pump design and compression pump design. Okay, when we have to use the floater pump design and when we have to use the compression pump design. By the way, there is some other category of assembly or construction called backed pump or semi-compression. It's not a popular in the market in industry, but it's existing. So instead of having all of the thrust is transferred to this the seal section, it's absorbed inside the pump. So after each couple of stages, there is a thrust already inside the ESP pump section, and it's absorbed inside the pump instead of transferring to the seal. But the impeller is free to move up and down, same as floater pump design. When you have a low profile application, when you have a piece of cake well without a lot of problems, such as sand, such as gas, you have to go with the floater pump design. So the bottom line for any selection is to go to floater and don't complicate your design and to go to compression unless you have a necessary and really you need to go for compression, because compression will be better handling for sand, better handling for gas, because the impeller will not be going sit on the diffuser and it will not easy to be plugged in the compression pump design or stuck with the sand. As we spoke, since already with the impeller is free to move up and down, the only thing is to stop the impeller is the washer that already installed as illustrated on that schematic. This is the thrust washer that's supporting the thrust for each impeller. Why we have to use the floater pump? Since each stage handle its own thrust, a very large number of stages. So that's normally in a piece of cake application, on a simple application, without any having the need for compression, you have to go with the floater, and don't go for compression, because there is a risk on the compression is to have a human error, because there is some activity and the process should be done prior to dispatch the equipment to the field or prior to assembly on the field. Is called shimming. That shimming is to make sure the impeller is lifted with the proper value above the diffuser and not touching the diffuser bottom or the upper diffuser, and that could affect the problem. That process or action or procedure of shimming, it's something will not be discussed during our training because it's related to operation itself. But you have to know there is a risk of having the compression over the floater, and that risk should be mitigated and minimized if there is no need. Also, the floater pump cannot be utilized on the high rate application. So above almost 10,000 barrel, it will be difficult to have the pump assembled on the floater design, because when you have larger rate, higher application or higher rate, that means the weight of pump stages itself, it will be higher weight. So the diffuser itself cannot absorb the thrust for each impeller, and it should be transferred to the seal. So on higher rate application, the compression pump is the only applicable and available design is to be used. On that photo on floater impeller, just an illustration, the impeller is free to move up and down, as you can see on the schematic on the right hand. The impeller is free to move up and down. Okay. Between the impeller and diffuser, there is some force acting on the impeller. Those force is called thrust. Those thrust, in order to be mitigated, we should be aware of something called Esp Performance Curve. Let us go for that slide first and then back again. Yes. For each Esp pump, there is an Esp pump performance curve. That performance curve is indicate where we can operate the Esp. So for that one we present here, you can find the two black line, and in the middle it's in yellow. It's between 2,200 barrel fluid on the x-axis up to almost 4,700 on the upper limit. So with that pump, we can clearly identify from what is called operating range or ROR, recommended operating range. That pump can be utilized to produce production between 2,200 up to 4,700. Okay, if you need to operate that Esp less than 2,200, that will be operating on severe down thrust. If you need to operate the Esp above 4,700 barrel, that means your Esp is running on the up thrust operating condition. Okay, so when we talk about down thrust, that means your pump is running outside the operating range on the left hand side. When we talk about up thrust, that means your Esp is running outside the recommended operating range on the right hand side. Okay, with that we can go back for the thrust explanation, and you will be understand the explanation in a better way. Okay, so under normal operating condition, the fluid will go between the diffuser and the impeller, between the top and the bottom, and the pump will be running inside the recommended operating range. And the bottom line and the basic is to have a light to moderate down thrust on all Esp stages, since the floater pump is already, the impeller is going down on the diffuser side. When the circulation force are greater on the upper shroud, that means the impeller is moved down, which called the down thrust. So when the circulation force greater on the upper shroud, it's mean down thrust. When the recirculation force are greater on the lower shroud, the impeller is moved up, which means we are running on the up thrust condition. Okay, that will be the explanation under normal operating condition. You can see the impeller and diffuser is running almost in a good shape, and there is no any contact between the impeller and diffuser on the normal operating condition. Okay, the surface area for the upper shroud is larger than the surface area for the lower shroud. Everyone already aware what means shroud, upper shroud and lower shroud. we already explained on the impeller and diffuser component. The top part, this is the upper shroud, and the bottom part, this is the lower shroud. So when the circulation force on the upper and lower shroud is almost equal, okay, or the upper is little bit higher, the pump will running on the normal operating condition, okay. But because of the larger cross-sectional area on the upper shroud, that means the impeller will be moved down, okay. Is that clear? The cross-sectional area for the upper shroud is higher than the lower shroud cross-sectional area. So the normal is to have the impeller is going to be moved down. Okay. At some point, the fluid is going into the pump will lift the impeller up. Okay. Because of the energy of the reservoir itself. So that means the pump, the impeller will be overcome to be operating on the down thrust. Okay. So with that means the pump will going to operate in the up thrust condition because the force going from the bottom is higher than the gravity force going from the up. Okay, this creates a larger cross-section area on the bottom shroud, which increase the pressure, and that cause the impeller to be going up, which is called up thrust. Okay, but on the other side, when you have the energy from reservoir is less than the upper gravity force, that means your pump will be running in the down thrust. Okay. The highlighted on the schematic on the right side, this is the washer that's supporting the impeller thrust to be absorbed in the down thrust washer or the up thrust washer. The up thrust washer is used between the ESP stages, and the down thrust washer will be used in the bottom of ESP stages and the diffuser as well. Okay, in order to evaluate the pump performance, there is a three main identification to identify the efficiency for each ESP system. Number one is the head. If you look for the recommended operating range and the ESP performance curve, you can see the head capacity, which is the top one, and then the pump efficiency, okay, and the brake horsepower line as well, which started from almost 10. Okay. In order to identify the pump performance, as we already identified, you have to identify by head and flow rate and brake horsepower. With those, you have to calculate the efficiency either in hydraulic horsepower and efficiency as well. The equation for hydraulic horsepower is to multiply the head in terms of feet, multiplied by the barrel per day, and multiplied by the specific gravity of the fluid, and then to get the efficiency, you have to divide the hydraulic horsepower by the brake horsepower. This is an exercise to how to calculate the efficiency. If we assume the head per stage is almost 42 feet per stage, and the flow rate is 4,000 barrels per day, and the brake horsepower for on the motor side is 1.8 brake horsepower, and the specific gravity of the produced fluid is 1. So the hydraulic horsepower will be multiplied of 42 multiplied by 4,000 barrel flow per day multiplied by the specific gravity divided by 6,000. Okay, that you get as the hydraulic horsepower is 1.23, and you will divide it by 1.8, which is the brake horsepower. That means your efficiency is almost 86.6, which is close to 70%. With that, we close the pump section, and I will recap quickly the ESP pump component. The ESP pump component is the impeller and diffuser and shaft and housing. Each impeller is connected with its diffuser together inside the housing, connected from the top with charge head, connected from the bottom with the intake or another section pump, impeller and diffuser having 3 category in terms of hydraulic design, radial and axial and mixed. Radial is 90-degree busway for the flow, while the mixed is almost 45-degree. Radial is utilized on low rate and when you don't have any plugging possibility, and it's almost also used when you have the needs for production optimization. And mixed flow utilized when you have high gas, high sand content, possibility of plugging, and higher rate as well. In terms of construction, there is 2 categories, either floater or compression. You have to be low profile as possible and install the floater on any application unless you have a necessary to install the compression. So you have to go with the compression to mitigate if you have sand or plugging and you have the need for compression pump. Also, compression pump utilized when you have a higher rate because of the thrust cannot be handled on the floater design. Okay, and we discuss also the thrust, the down thrust and up thrust, why it's existing and how to mitigate, and the recommended operating range, what it's mean, and what is the factor affecting the ESP efficiency and how to calculate the ESP efficiency as well. Any question before we go to other component of the ESP? Okay.
You can see this question in the chat box.
Difference between gas handler versus gas separator in the diagram. Okay, gas separator is used to separate the gas to the casing or to the annulus. So when you talk about gas separation, you will utilize gas separator. The gas separator will be connected directly to the bottom of the pump. Okay, gas separator can be used when you have the casing is open to the flare or to the flow line. But if you have a closed casing or if you have a non-vented bucker on the annulus, you cannot use the gas separator. Gas handler is used to handle the gas, is to increase the capability of the system, is to handle the gas. So the gas will not be separated. The gas will be going into solution with the oil in order to be handled with the pump. So the gas handler will be connected directly to the bottom of the pump. Okay. This is regarding the first question about the difference between gas handler versus the gas separator. Is it normal to see signs of down thrust on the stages, missing or damaged washer in a pull out compression pump? If not, what could be the reason? For compression pump, you shouldn't see a severe effect on the thrust washer. The missing or damage, no, absolutely you shouldn't have missing or damage. You can have a slight wear, you can have a slight effect, but to have missing or damage, absolutely it shouldn't be available at all during pull out of all. So the reason for that, it will be wrong installation, either during workshop assembly or field assembly. Either it's missed at all during assembly, or it is installed in a wrong way due to the shimming calculation, which we explained. There is a shimming procedure should be followed, and that should be calculated in a proper way in order to avoid going to either above the required value of shimming, which is called over shimming, or less shimming. So at that case, the most reason will be realistic for your case will be the less shimming amount, so the impeller is going in directly with the diffuser that's caused the damage washer. Okay. Is there a modification to the problem of pulling the tubing out of the hole for pump surface? Is there a modification to the problem of pulling the tubing out of the hole for pump surface? Yes, we discussed initially that some of the limitation for ESP is you have to pull the tubing on each workover. Nowadays, there is a lot of companies, and Baker Hughes, one of those companies, is to having a rigless ESP system. Rigless ESP system, that means it's installed without the rig. Okay, but in order to make sure you can utilize those system, the rig should be visit the well for the first time. That means for the first installation, you have to use the rig, and then you will not be in need for the rig. But the cost for those equipment versus workover should be calculated in order to make it to make sure that's an efficient system, because the cost for rigless system is almost can reach 3 to 4 times the cost for conventional ESP system. And also the rigless ESP system is limited in terms of production rate. ESP can go up to more than 1,000 barrel fluid per day, while the rigless system is still limited in terms of capability. It cannot reach to the higher rate value. That's all the question on the chat. Please keep placing your question on the chat. We'll go for that after each section to explain any unclear point. Okay. The second part on ESP pump is the intake. By simple, the intake is just a port, provide the pathway for the fluid from the reservoir, from the perforation to the ESP pump. So there is no any technology, there is no any a lot of details on the intake. It's just an inlet for the fluid to go from the perforation to the ESP pump and connected flange to flange connection with the pump. Okay. On some application, when you have the intake is not enough to handle the pump is the ESP pump cannot handle the existing fluid in terms of gas handling, you have to install, instead of intake, you can install gas separator in order to separate the gas to the annulus before it goes to the ESP pump. Okay. The gas separator is coming into two categories, either a rotary gas separator or vortex gas separator. In order to explain the theory of operation for each type and when you have to use each type, on all wells with high gas oil ratio, rotary gas separator replace the standard pump intake, and it's improve the pump performance by separating those free gas before it goes to the pump, and that also eliminate the phenomena of gas locking, which extends the run life of entire ESP system. Okay, so let us know what happened to the gas when it reached to the top and how it affects the operation. All of you already aware that the bubble point is the point of pressure at which the gas start to break out from the liquid and start to be free and not coming into the solution. Okay, when that free gas is present in the fluid in a well running with ESP, the pump should be able to handle the gas. Otherwise, the pump will be going to be locked and cannot handle the flow. On the let us know how and when and how does the gas locking occur. On that schematic, okay, in a mixture of gas and liquid, okay, is going through the standard pump impeller, and the pressure in such the density difference between the gas and the oil, the gas will tend to accumulate behind the impeller van, okay? And in the area of the lowest pressure in the impeller, the liquid flow will not be able to drag the gas accumulation out of the low pressure, okay? Under that condition, the gas will start to be accumulated as shown in the photos on the right hand side, okay? With that, this design, okay, is applied for both radial and mixed flow stages in order to improve the gas handling. Okay, so what will be the solution in order to solve that, and what will be the next if it started to have that accumulation of free gas in the impeller? What will be the next if you keep that gas is completely to fill the area of I? It will be it will completely fill the area of the impeller until gas locking will be occur. But when enough gas is present in the impeller, the gas will tend to accumulate even more near to the eye of the impeller, because centrifugal force will tend to send the higher density liquid to the impeller outer diameter, while the gas will be inside, near to the eye. At some point, the gas obstruct the eye completely and no longer let the liquid enter to the eye. In that schematic, you can show a fairly clear separation between the liquid and the gas. This is not an actual true, but it's imagination of what happened inside the process of gas locking, and in which the liquid and the gas mixture will not be interfaced in dynamic operation. The gas liquid condition will last until the pressure change occur, and then will be broke, and the charge or intake the impeller while that occurs is actually happened manually or automatically. Okay. There is two types of gas separator, which is rotary and vortex gas separator. The first one is the rotary. The component is the intake and shaft and inducer and rotor and guide van and gas vent van. The inducer, which is the rotating part, that separates the fluid to the outer surface, and the gas naturally stay in the middle. Okay, the separation is further supported by the paddle, that part. Okay, which puts the fluid upward and to the outer surface. The inducer, or in abbreviation, it's called HAVA. HAVA, it's HAVA. It's a Baker use abbreviation for the inducer. Okay. Almost the gas separator, it's consumed between 2 to 1 horsepower during the ESP sizing. The rotary gas separator almost rely on centrifugal force created by the rotating chamber to separate the fluid. The rotor force the heavier fluid to the outer diameter of the chamber, and the gas remain inside, as we explained on the previous slide. And then the gas will be vented out through the port, and the fluid is routed from the outside of the separation chamber to the inside of the pump. That rotary gas separator is suitable for viscous application. So when you have a viscous application, the rotary gas separator will be applicable for that. It's the same component for vortex gas separator, almost close to the rotary, but the only difference is the high angle for inducer. So you can see the inducer is having high angle van, which Baker Hughes abbreviation have a high angle van angle. The inducer does all the separation for fluid. It comes in a better for abrasive application. So Vortex, it's a better when you have an abrasive application. Due to that design, okay, the inducer compared to the older one, which is the rotary, on the rotary one, you might have an gas separator cut, you might have an failure, mechanical failure with the gas separator due to the abrasive. But with Vortex, when you have abrasive, you have to use the Vortex. Also, Vortex is much applicable when you have higher gas volume. The theory for operation for Vortex, using the inducer to induce the vortex in the fluid, utilize the natural separation through the vortex motion to separate the fluid. And this naturally less gas will remain at the center. By that, the majority of the gas will be separated outer and goes to the casing. And as we explained, it's suitable for high rate application and for abrasive condition as well. Just some photos between the old intake and the new intake. It's only the difference is the port. If you look for the port is wide, narrow in the old intake, while the new intake, the port was wider and having an angle, which will decrease the possibility of plugging for the intake ports. Same for the old discharge. The old one is the port for charge is narrow and straight, while the new one is making almost 45-degree and wide enough to make the flow homogeneous and not making to have a turbulence effect on that area. Okay, same for the old and the new design for gas separator inducer. The upper one is the old and the bottom one is the new. You can see the high angle for the bottom one, which make a better handling for the gas, and less gas will remain on the middle, while the majority of the gas will go to the casing. With that, we close the intake device, whatever it's intake or gas separator. We have to highlight that in terms of talk about gas handling, there is a lot of topics can be discussed in terms of gas handler, multi-phase pump, gas insurance, all of those tools or equipment. It's not a standard equipment while we are talking here about the basics. So in terms of basics, that's enough, is to have the information about the intake and the gas separator. In terms of having more technical discussion and technology on the gas handling, it could be another session, because it takes more time to explain the difference between multi-phase pump, gas handling, gas insurance, when you have to use each one of those. But in terms of basics, that's enough. Then we will go to the seal section, which is the most important part of the ESP equipment. We'll take those two questions, and then we will go for the seal section. Can the pump installed in the power cable? There is an application for Baker Hughes called cable deployed system. So the ESP, the power cable is utilized as power cable and carrier cable at the same time. Approximately almost 3 systems installed in Saudi Arabia with Aramco, and this is existing application for installing the pump with the power cable. How can we overcome the gas leaking issue if it's occurred? Okay, this is almost will be a topic related to troubleshooting and overcoming the gas leaking. I would like to grab the attention for the people here. Most of the attendees is student still in the faculty of engineering, and they still interested to learn about the basics of ESP. while if we have to talk about overcoming the gas locking, we will go for troubleshooting and other topics which might not be the suitable time and place to discuss that. Can you highlight motor cooling method, bag and labyrinth? You are in hurry, man. We just going to the seal and you're asking about the motor and bag and labyrinth. Be patient. We still going to the seal section and going to that part. Okay. Okay. Seal section. It's the most important part of ESV equipment, and it's coming connected to the intake device from the top and connected to the motor from the bottom. Okay, so it's located between the pump and motor. In a bullet, okay, we will have to discuss what was the function for motor seal. Baker Hughes called it seal, while some other ESV provider called it protector. So you can hear from other instructor or from other engineers, protector, not seal section. So it depends on his background and his company. So the main four function of ESB seal is isolation, expansion, equalization, and absorb the pump thrust. So in general, you have to deal like that. If you have been asked what was the function of ESB seal, you have to put it on a bullet line. Don't elaborate. Just isolation, expansion, equalization, and absorb the pump thrust. If you require to have more clarification, so we will have to go for each one of those functions and explain in detail what was the meaning of isolation and expansion and equalization and absorb the pump thrust. Okay, the first one is the isolation. The motor, if we go to the motor, it cannot, this is the motor section and pump section. Imagine if we have to connect both of those sections together. So we'll have the pump on the top and the motor on the bottom. So, and we need to connect it together directly without any other parts in between. So here, the function of the seal is to transfer the torque of the motor shaft to the pump shaft. So this is the first one, is to transfer the torque of the motor shaft to the pump shaft. Okay? So transferring the motor torque to the pump shaft, this is the first one. So we will not have the motor connected to the pump directly. As you can see here, okay, if we connected the two shafts together, the two components that produce our fluid is the motor and pump, and the motor shaft turns the impeller. And if we could just couple them together, the shaft torque would go directly from the motor shaft to the pump shaft. Okay, and this spot of connection will be having a higher torque existing, will be higher risk point. And however, the seal provide many important functions to protect the motor, so we must have it. By having the coupling between the shaft of motor and the shaft of the seal, okay, we will eliminate that risk and having that connected in a proper way. So the first main function of seal is isolation. Okay, this diagram you can see here is explaining what would happen if we couple our equipment together and placed into the well. So that means the fluid for the pump will be connected directly to the motor because there is no any isolation between the motor and pump. So the well fluid will go to the pump while it's already connected to the motor. Well fluid will goes on the top of the motor and lead to have a burned motor immediately. Okay, so you have to think about it, why it's bad, and we cannot connect it together directly, the pump and the motor, because the oil fluid would enter the top of the motor and burn the motor immediately. So isolation is to isolate the clean motor oil from well fluid. So well fluid shouldn't go through the motor. So this is a function of seal section. In that picture, we will explode the seal section Labyrinth Chamber. Okay, the seal section having two types of chamber. The first one is called Labyrinth, and second one called bag. Okay, so the Labyrinth chamber is provide a separation of well fluid from the motor by gravity. So the fluid going from the bottom on the picture, this is the motor oil. So all the green is the motor oil and seal oil, while the other fluid with the dark color coming from the top, this is the well fluid. So when you have that well fluid is going inside the labyrinth, that means that well fluid is kept away from the motor. By another explanation on that pictures, the well fluid will enter the top of labyrinth chamber, and the difference in specific gravity will cause the well fluid to sink to the bottom. So the well fluid will go on the bottom of the chamber, while that work because in order to contaminate the next lower chamber to the well fluid must displace a lighter fluid and migrate upward against the gravity in order to gain access to communicate the next chamber. Okay, so all of that is well fluid. Okay, while this is the lighter one, while the heavier one is the dark fluid, which is the well fluid. Because of its higher gravity, so it goes to the bottom. So you will keep all the way the lighter oil, which is the main fluid for motor and seal, away from well fluid. So it's all about the gravity, all about the gravity separation. This photo from reality explaining the well fluid, the motor oil and labyrinth section and communication between the labyrinth section and top part. So this is actual view. This two section connected together, two labyrinths connected together. So the fluid was going from the bottom. This is the motor fluid, is going all the way up, fill all the labyrinth chamber, and goes in connection between the bottom chamber and the upper chamber. And the dark fluid, this is the well fluid. You can see the dark fluid is only having low volume in the bottom of the top chamber because it's higher gravity, so it goes to the bottom. So with that, we almost clarify the labyrinth chamber theory of operation and also clarify what it means isolate the well fluid from the motor fluid. This is how the labyrinth work due to the job of isolation, and this is only way which the seal section provide isolation. There is a couple more ways in which the fluid can enter or migrate down into the motor, and one of those way is down the shaft. Yes, this is the photo that explains the way of having the fluid going all the way through the shaft. This is one of the main component for ESP motor seal, which called the mechanical seal. This mechanical seal provide a well fluid isolation on the top of the shaft. So this is a photo of mechanical seal. On such photos for motor seal, on the right hand side, there is 3 chamber. Okay, those 3 chamber having a 3 mechanical seal. Let us go back for the Labyrinth Chamber for a bit to have a relatively straight clarification of labyrinths on deviated well. Imagine if you have that labyrinth section on deviated application. Are you still having the function of gravity if you have that labyrinth in deviated or horizontal application? For sure not, because the function of the gravity depending almost on vertical position for labyrinth section. So if you have a deviated well or nearly horizontal well, you cannot install the labyrinth section. And according to API, above 30-degree inclination, you have not to install the labyrinth. That's according to API recommended practice. On many applications, it's proven that maybe above that number can install, but for sure it will be installed in combined with another chamber, not only labyrinths at all. As we explained, there is 2 types of chambers. The first one is the labyrinth, and second one is the bag system. So in that chamber, the bag is a rubber element. That rubber element is expanded with the heat of oil during the operation. So if you go on operation and start to have the oil and fluid of the motor was heated up, that bag will be shrinked in order to have a bigger volume to withstand the higher volume of the motor oil. And that back chamber will not be affected by deviation. So this is will be the replacement or the most proper plan for having the seal chamber on the deviated well. And that will be the second function of the motor seal, is to have the expansion during the operation. That bag will be expanded during heating and will be contracted during the cooling. So that bag will provide an area for motor oil expansion volume, and will making as well as the expansion is the reason we don't use tougher material. The bag will be rubber material, such as sometimes HSN or AFLAS material. So harder material is not suitable for bag. Sometimes on high temperature applications, there is something called below metal bag, but it's not purely metal. It's something like a spring. So it provides the function of expansion without being affected from the high temperature application. That elastomer bag is stretch, allowing for motor oil to expand with its bag without escaping of the oil. Once that pressure inside the bag will be reach a certain point, the oil will be released into the well through a one-way check valve. That check valve will be on the top. So the back section will be installed in application when we have deviation, when we have high temperature, when in reality the seal section in industry it coming in most cases on 3 chamber. So the ESP providers having multiple design for seal section is to have one labyrinth at the top, for example, and 2 bags in the middle and the bottom. Those bags can be connected either in series or in parallel. So in series, that's mean each bag section is acting as a single chamber isolated from the second or third chamber. Parallel, which mean both chamber are connected together and the fluid can go between both chamber without isolation between both of them. And that configuration or combination can be vary or changed based on each application. Sometimes you can have only 3 bags without labyrinth at all. Sometimes you can have the bag at the top and labyrinth at the bottom. Based on each application, you have to use your proper configuration of the seal section. And you shouldn't have that standardized unless you have your field and experience and wells identical, or the difference is not critical to have it standard along your field. So you have to consider for each application the proper seal configuration based on your application. In the bearing assembly that showed in that photo, this is the bottom section for seal section, the bottom chamber for seal section. The bottom chamber is acting on the force function of the ESP seal, which is the absorption of the thrust created by the pump, impeller, and diffuser, impeller, and the shaft of the entire ESP equipment. Those bearing ESP assembly is having the bearing runner and upthrust bearing, and that bearing responsible to have the function of absorbing the thrust. If you look for these photos, for example, this is an example of bold thrust and runner affected by thrust transfer from the entire ESP system to the thrust bearing of the ESP seal section as well. In that photos, we will have explanation animation of how the fluid goes between the motor and seal section and how it's critical to prevent the immediate failure of contamination. Okay. In that configuration, you have the top section was labyrinth, and the second one was the bag connected in parallel with another bag. When we talk in parallel, that's mean both bag sections, the second and third chamber, is connected together. Okay, so when you have start your ESP system, the temperature goes up, so the fluid from the motor will goes inside the bag chamber, and bag will be expanded and then goes to the second bag and expanded as well, and it goes to the well fluid to out to the well fluid. So the amount of fluid will be going outside the protector or seal section. And once you make and stop, the bag will be contracted and amount of well fluid will goes inside the labyrinth section and will goes on the outer volume of the bag, will not go to the entire volume of the bag section because the entire bag is connected through the shaft, through the mechanical seal, and that's supposed to be running efficient and isolating the well fluid is to goes to the entire bag. So if you have again a start, the same process will be happened again. Will motor oil will goes up to the bag will be expanded, and some of the motor oil will goes to the outer of the seal section, and the labyrinth will be accumulate. Once you have the stop, another amount of well fluid will goes inside the labyrinth section until that labyrinth section will be fully completed with the well fluid, and those bag will be contracted and get less and less in size because of the a lot of start and stop, and then we will have a failure for the seal section. So that seal section is provide a long run life through the reservoir of oil that can compensate the loss of motor oil to the well bore. So without having that seal section, if you have just the motor connected to the well fluid, it will contaminate with the oil fluid and also will have no compensation for the lost oil due to expansion of the motor oil due to the heat. Due to that heat, and the well fluid will go into the bag, and then the mechanical seal will be failed or the bag will be failed, and then you will have an ESP failure due to the water invade or well fluid goes to the motor and the motor will get burned. With that, we closed the seal section, and I will check if we have what will happen to the fluid that has been accumulated inside the seal. What has been accumulated inside the seal. The fluid will accumulate it inside the seal section. If it's labyrinth section, it will go to the bottom by gravity. So there is no any effect on the ECB system if we have the labyrinth on the top or labyrinth section. And even if we have bags, the fluid will goes on the outer volume of the seal chamber having the bag, will not go inside the bag section. So the ECB seal section is designed to have isolation from the well fluid to the motor oil and seal oil, which is inside the bag or inside the labyrinth by gravity or by the isolation. So there is no any risk of having the well fluid inside the seal section unless the labyrinth section it goes completely filled with the well fluid. Then it will go to the second chamber and having dangerous of contaminated with the motor oil. Please, seal filling and the drainage procedure. That training is ECB basics training. We didn't go for installation and procedure for filling, and that sealing, filling and drainage procedure is different from company to company, and that's something shouldn't be shared in public with unless you have unless you are a customer for our ECB company, so you can have that procedure handy to you. How we can monitor motor oil level and to check contamination. How we can monitor motor oil level. The motor oil is not monitored by level, is monitored by temperature. So whenever you have a good motor temperature, that means you have an excellent motor oil level. Once you have your motor temperature is going up, that means you might have one of the problem is related to motor oil. So there is no direct parameter or indication for oil level, but there is associated parameter can lead you to explain what is the condition of the motor, is that healthy or not, and to check if it's contaminated or not. Actually, once your motor oil got contaminated with well fluid, it will not sustain for a longer time. It will short in a couple of days. It will not run for a longer time. So no need to have to check the contamination, because once you have the contamination, you will be failed. So there is no benefits to have it, the contamination check. People, are you okay to have 5-minute stretching and relaxing, and then we will continue with the ECB motor? We almost have 1 hour and 10 minutes, so we have almost 20 minutes to close. Okay, let us have 2 minutes stretching. You can, if you're sitting on your chair, or just stand up and stretch your legs and stretch your hand, make some exercise, and within 2 minutes we will go back again.
Okay.
In the ECB industry, we are using an AC induction type design. So we are using AC induction type design. That in the normal ESB industry, we having that motor rotate at approximately 60 hertz or 3,500 RPM. That equivalent to 50 hertz, 2,917 RPM. Is constructed of rotor and bearing stacked on the shaft and loaded on the stator. The motor is contained a synthetic oil for lubricant and rely on the fluid flow path across the motor to make a cooling for the motor itself. There is 2 types of ECB motors: the induction motor, and nowadays there is another type of motor called permanent magnet motor, running at higher RPM or higher speed. And there is another, but you shouldn't be we shouldn't be discussing the permanent magnet motor on our session today. We will just focus on the main basic ECB motor component, which we already explained: the rotor and the stator. That rotor is and the bearing is stacked onto the shaft and loaded into the stator. This is a photo explain the stator is made of lamination stacked together, and the stator lamination same thing with the rotor, and the rotor is stacked with the lamination as provided on the in that photo. The lamination for the stator is stacked together and compressed in the housing, approximately almost large copper bars and more magnet wire in the stator. This is almost the slide to describe the air gap between the rotor and the stator, and talk about the key ring bearing and its purpose. As a student, you don't need to have more details on that slide, and the component for bearing and for key ring. Okay. The main driving factor and operating temperature is determined by 5 factors. The wellbore temperature, which is the reservoir temperature. So if you have a motor need to be designed for a wellbore temperature 200 F, so you shouldn't go to select a motor with temperature rating 200 F. And if you have motor operating to be operated in well condition with 300 F, so you should consider a motor with 400 F. So you should consider your motor rating higher than your downhole well temperature. The load and nameplate rating. Your motor load should be all the time between 60 to 70% from your nameplate, and considering your future needs or future forecasting for the operating condition. Okay, in reality and best practice, according to API recommended practice, you should have a fluid velocity passed across the motor for 1 feet per second. Okay, this is vary between condition to other and will condition to other. Can be less than 1 feet per second, but it's function of what was your motor load, what was your production rate, what was the internal temperature, what was your fluid that you are producing. Do you have a scale? Do you have wax? Do you have viscous? Do you have gas or not? All of that condition could affect your answer on the required fluid velocity. But according to API, you should have 1 feet per second fluid velocity past the motors. And as I said, that cooling will be vary between the percentage of gas, water cut, and scaling. And one of the main also factor on the motor operating parameter is the power quality. If you have the motor will be specified by three numbers. Number one is the horsepower, and number two is the volt, and number three is the amp. So when you have to select your motors, if you look, for example, for 60 horsepower motors, you can find there is 2 volt. One is 805 over 48 amp, and another one 910 over 42. With that, there is 2 volt and 2 amp. Normally, in terms of selecting the motor, you have to go for the higher volt, low amp. It is the best in practice is to select the higher volt, low amp. So almost to go for higher volt, low amp. Don't go for the lower volt. Why? Because the higher volt will give you a higher torque that will eliminate the stuck during the startup, or if you have any stuck during the operation, so it will give you higher torque, and which will allow you to free your pump from any stuck. And number two, if you have low amp, that means you will have a less cable cost, because the lower cable size, that means the lower cable cost, which is too much difference between size 1 and size 2 and size 4 cable. And also, if you have higher volt, low amp, that means your voltage drop can be compensated easily, and the only limitation is to have the higher volt, low amp is your surface equipment. So if you have your surface equipment rated up to 3000 kilovolt and your motor is almost above 3000, you shouldn't go for the motor. You should stick with your existing surface equipment limitation. Okay, quickly we will go to the power cable. The power cable can be coming either in the flat or round or flat. If you can see in the photos, the round is having a better mechanical properties and mechanical handling and physical capability, while the flat will be less. Because in round, as you can see, let us go for the second slide and get an explanation of the main component of ECB cable. Yes. The outer one is the conductor. The outer one is the armor. So the armor is number 4. Okay. That armor is coming in different material: galvanized, stainless steel, and monel. Galvanized is the most common one, and it's used on the application while you don't have a corrosion issue, high salinity, H2S, so you can go with galvanized. Stainless steel, it's excellent handling for corrosion and chloride at low temperature. So if you have a temperature less than 160 F, you can use the stainless steel. If you have a H2S, if you have a higher salinity fluid and higher temperature, you have to go to monel cable. But for sure, monel is higher cost than stainless steel and galvanized. And then number 3 is a jacket. That jacket is coming in 2 different material, either nitrile or EPDM. each one of those material having advantage and disadvantage over the other, and you selecting based on your application and your needs. And number two is the insulation. Those insulation also coming in two different material, either EPDM or polypropylene. The most common material nowadays in the oil industry is the EPDM. So the EPDM is used in the jacket and used in insulation material as well. And each one of those material have a temperature limitation as well. The conductor, which will be in copper for sure. Okay, so this is a schematic for and the component for round cable. For flat cable, it's almost the same component, but without the jacket that we already explained on the round cable. Okay, so the OD for round cable will be bigger than the flat cable. So if you have a clearance issue, so you can use the flat cable. If you have and cost associated concern, so you can use the flat cable if you have a cost issue, because the flat cable is less than the round cable in terms of cost. Okay, but sometimes the cable is coming in three different, the conductor is coming in three different category, either solid, okay, same like the photos on the left hand side, or stranded, same like the one in the middle, or compact stranded like the one on the right hand side. So the solid, the conductor is coming on only single bar, not divided, okay, and bigger OD. And stranded, it's divided on almost 7 copper bar, and compact stranded is same like stranded, but it's compacted for less and smaller size. Okay, in some application, when you require the chemical injection, you can have a chemical injection installed with the cable, and you'll have either one armor or two armor, same like the photos on the right hand, the first two photos on the right hand, from the right hand side. You have a chemical tube is installed inside the power cable, is to deliver the chemical to the bottom. Well, this is quickly one of the issue on the cable itself that might affect the cable is called the decompression. That phenomena is happened during the gas venting from the annulus to the surface. If you have to, if you already pulling your gas very fast from the annulus, so you might affect the integrity of the jacket, and that might affect to have a crack on the jacket. It shouldn't be on that training, because it's more extensive on the phenomena of that decompression. Anyway, just we need to highlight that the MLE, which is the motor lead extension, this is the part connected between the motor and the power cable, and that's almost is flat, only flat. It's not in round. So the motor lead extension is the same component for flat cable, conductor and insulation and armor, and only connected between the motor and the power cable. Normally, the power cable is installed from the surface up to the first tube, mid of the first tubing above the charge head of the pump, and then the MLE or motor lead extension will be connected from the middle of the first tubing up to the motor head. There is a one more component on some other application. If you have high H2S or high gas content, and you need to have to protect your insulation and conductor from high H2S or gas, you are using something called lead cable. If you look for number 3, this is a lead sheath. Okay, this lead sheath is preventing the gas, and H2S is to attack your conductor and your insulation as well. So that type of lead cable is installed only on high and severe gas condition and H2S attack as well. So quickly, this is the power application of ESP cable, round and flat. We already explained the issue of clearance. If you have an issue with clearance, you have to go with the round versus the flat. With that, we almost finalize the cable. The remaining is the downhole sensor and the surface equipment. We have almost 5 minutes to close. I will go quickly through the ESP, the question on the chat, and we might arrange for another session to continue the remaining topic on that session. We are on the session since 90 minutes. Okay, I see most of the people. It's already scheduled for 2 hours. Maybe in the upcoming session, it could be scheduled only for 1.5 hours instead of 2 hours. I see that most of the people is by end of the day they are coming not interested. Okay. Anyway, we are finalizing most of the ESP equipment, and we still having the downhole sensor and surface equipment that might be completed in another session. Any other question before we close the session? Thanks for your attendance. Thanks for your patience, and hope that is an informative session, and I have already succeeded to add some information for you.
بنشكرك جدا يا باشمهندس على السيشن الرائع والمفيد جدا. شباب، أي حد عنده أسئلة يكتبها في الشات بوكس أو يعمل ريز هاند.